Current electricity is the most convenient form of energy transfer. It is everywhere. In the years before electricity, trains ran on steam, household lighting relied on candles, heating was by firewood, and communication over long distances was simply a nightmare.
Mankind's technological abilities grew rapidly after the discovery of the use of electricity. But why electricity? Well, electricity is used because it is safe and easy to transmit across vast distances. What is the property of electricity that allows it to be exploited this way? Well, in order to answer that, we need to look at what electricity is made up of.
Technically, there are two forms of electricity: static and current. In everyday use, the word electricity usually just refers to current electricity. Electricity is the flow of negatively charged particles called electrons. Electrons are components of atoms, the building blocks of matter. They are negatively charged and incredibly light. Current electricity is the flow of electrons carrying energy from one point to another. It is as if the electrons are messengers scurrying back and forth with energy from source to the sink. In looking at how useful electricity is, an obvious question comes up. Why electricity, as opposed to some other form of transmission of energy? The answer is simple. It can be converted from one form to another very easily. Just take a look at this display. We begin by turning the wheel. We are supplying mechanical energy. This is then converted to electrical energy. In the final step, the electricity is converted back into mechanical energy as the fan blades turn. Of course, this does not apply only to mechanical energy. As we can see, light and sound energy can also be converted back and forth just as easily.
Some property is needed to determine how much energy is given to each electron to travel from one point to another. This is what is known as voltage or potential difference. Anytime a potential difference appears between 2 points with a conducting material in between, current will flow. Current can come from the oddest places. A potato can be used as a low voltage battery. So too can your hands. This is because the moisture in your hands acts as an electrolyte, and your body completes the circuit between the copper and the zinc electrodes. Although we did see a deflection here at the hand battery, its strength was almost negligible. It was to the order of microamperes of current, which is hardly enough to power anything. We need to find some device that can create electricity in sufficient quantities to be useful. Electrons cannot flow as electricity in isolation. They need a medium, something to flow through. That's what a conductor is. Metals are excellent conductors of electricity because they allow electrons to pass rapidly from one point on their surface to another, with very little hindrance or resistance to their flow. This is why wires are made of metals like copper. Insulators, on the other hand, materials like wood, plastic, or acrylic, do not allow electrons to flow. They have a very high resistance. From our everyday experience, we know that any fast-moving object has to deal with friction, which tends to heat things up and slow them down.
A similar thing happens in electrical circuits. Resistance in electric circuits acts similarly to how friction works on everyday objects. The higher the resistance to flow, the more energy is lost as electricity passes. Here, at this display, we see that by adding a few ball bearings to the wheel on the left, it spins longer than the wheel on the right. This is because the wheel on the right is subject to more friction.
Now, if we move over to the right side of this display, we see something similar happening in a circuit. Without the resistance, the bulb glows brightly. But if there is some resistance in between, the electrons reaching the bulb are less energetic, so it glows less brightly. This is what an actual resistor in a circuit looks like. Notice that it has color bands on it. These color bands represent its resistance. different values of resistance correspond to different color bands. So given a resistor, how do we know how much current is flowing through it? Ohm's law comes to our rescue. But before we get into Ohm's law, we need to understand the difference between voltage and current. Current is a measure of the number of electrons that pass through a given point in the circuit in unit time. Voltage, on the other hand, is a measure of the energy of each individual electron in a circuit. The two of them are related by Ohm's law, which states that the voltage is directly proportional to the current. The unit of current is the ampere, the unit of resistance is the ohm, and the unit of voltage is the volt. Now if we want to calculate the current flowing through a given resistor, we simply use the formula current is equal to voltage divided by resistance. Potential difference to electrons acts exactly like gravitational potential to this water. So if something's at a lower potential, the electrons have lower energy. In this analogy, at position A, the water has less energy to turn the turbine, but if I move it up to position B, the gravitational potential energy increases and the turbine turns faster. This is the same thing that happens when a potential difference is increased. The electrons move faster. If we now move over to the circuit, we see that as we increase the voltage, the electrons have more energy, so the bulb glows brighter. As we decrease the voltage, the electrons have less energy, and the bulb is dimmer. Alessandro Volta invented, among many other things, the voltaic pile, which was the first battery as shown here. Built in 1800, Volta's pile was a series of galvanic cells connected together so that their effects combined. So how does each galvanic cell work? In order to understand how it works, we need to do a little chemistry. A galvanic cell is an example of a simple battery. The setup consists of a piece of zinc in a solution of zinc sulfate and a piece of copper in a solution of copper sulfate. The two solutions are in separate beakers, so to complete the circuit, we use a salt bridge, which consists of sodium and chloride ions. A voltmeter is connected across the copper and zinc plates to detect any potential difference. Zinc, as a metal, has a tendency to lose electrons from its atoms. The atoms turn into positively charged ions and become part of the zinc sulfate solution. The electrons pass through the wire, through the voltmeter, and onto the copper plate, making the copper plate negatively charged. Copper ions present in the copper sulfate solution absorb these electrons and turn into copper metal. This leaves excess negative sulfate ions in the solution, which are neutralized by the positive sodium ions from the salt bridge. On the zinc side, the excess positive zinc ions which build up are neutralized by the negative chloride ions from the salt bridge. The reaction stops when either the zinc plate or the copper ions are depleted. Since there's a transfer of electrons here, there is technically a flow of current. This is the principle that Galvani discovered and Volta later built on. This flow of electricity is appreciable in a large enough pile of copper and zinc cells, and this is the way a Volta's pile is created. In theory, this is a good enough battery, but practically speaking, nobody can use a battery this large. It also has a liquid electrolyte, which is especially difficult and impractical to have to handle. And can you imagine placing a battery of that size into a camera or a cell phone?
Luckily, battery construction has improved over the years to the point where batteries today can be very small. As demonstrated here, batteries of different sizes and voltages can be created using different metals such as lithium and different electrolytes. However much the construction may change and the materials may have been replaced and refined, the concept behind the generation of current electricity through batteries is still pretty much the same as it was in Volta's time. As a recognition of his contribution to science and technology, the unit of potential difference is called the volt. That word has become so common that the word voltage is used more often than the phrase potential difference. There are two types of cells, primary and secondary. A primary cell is an electric cell in which the electrochemical reaction is not reversible. It stops working once its chemical energy has been used up. An example of a primary cell is an ordinary disposable cell like the type we use in a torch or a camera. A secondary cell is an electric cell which can store electrical energy and can be recharged. A common example is the rechargeable cell used in a mobile phone. The output voltage and current of the battery depends on the number of cells and how they are connected. In a circuit where positive terminals are connected to negative terminals, the voltages always add up, but the current does not. This is known as a series connection. The other way to connect the cells is to connect all the positive terminals to each other and all the negative terminals to each other and then complete the circuit. This is called a parallel connection. But this time, the current adds up. So, in this circuit with 3 batteries, we have a current of 3 amperes. But batteries are limited in their scope. The maximum voltage that can be created by a battery is not nearly enough to power even a small home. Although uninterrupted power supplies can take over the electricity required in a home for a few hours, it is impossible to sustain power generation for long enough using just batteries.
Just have a look at all the devices that run on electricity in one house. The electricity that powers our homes and offices needs to be generated at a very large scale in power plants. The problem is that energy cannot just be created out of nothing. A fundamental law in physics says that the total amount of mass and energy in the universe is constant. This means that energy can only be converted from one form into another. Power plants, therefore, convert various forms of energy, such as thermal, potential, and nuclear energy, into electrical energy. But we'll have to wait for a while before we can delve into the actual mechanics of the generation of power on a large scale. The energy contained in electricity can depend on 2 things: the energy of each electron and the total number of electrons. So a certain amount of power can be achieved either by having few electrons with very high energy or lots of electrons with low energy. When transmitting power over long distances, it makes sense to have a small number of high energy electrons. This is because if more and more electrons are traveling through the wires, they are more likely to dissipate the energy as heat because they keep hitting each other. This is also why thinner wires need to be used, as demonstrated here by this analogy at the museum. This is an analogy with mechanics. We go back to our description of electricity flow as being like water flowing through a pipe. At the bottom, we have 2 tanks of equal size, but they are connected to the overhead tank by 2 different pipes. The pipe at the back has a diameter of 12 millimeters, while the one in front has a diameter of 10. It's not a huge difference, but as we see, the tank at the back fills up much quicker than the tank in front. This is because the larger pipe allows more water to flow into the tank in the same amount of time. Here in our circuit, we have 2 wires. Wire A is the thinner of the 2. If the same potential difference is applied across both wires, we see that the current in wire A is about half as much as it is in wire B. In wire A, it's about half an amp, whereas in wire B, it's closer to 1. The question then becomes, how do you increase the force driving the electrons through the wires? The answer to that question depends on what kind of current we're dealing with. Until now, we've imagined current to be a steady flow of electrons through a wire, like water through a pipe. This analogy describes a direct current. This is not the form of current that enters our houses. The electricity that enters our houses is an alternating current.
As the name suggests, an alternating current is one which goes back and forth between 2 extremes. What this means is that the energy carriers, the electrons, move back and forth in the wires instead of moving along in one direction. Don't worry though, the energy is still transferred in only one direction by being transferred from one set of oscillating electrons to the next. The number of times the current switches direction per second is called its frequency. The standard frequency for current at home is 50 Hz or 50 cycles per second.
The reason an alternating current is used is that its voltage can be increased or decreased as necessary very easily using transformers. Transformers use the principle that an electric field can induce a magnetic field, and vice versa. A simple transformer's job is either to step up or step down incoming voltage. In a step-up transformer, the secondary coil has many more coils than the primary coil. This allows us to increase the potential difference to very high levels for power transfer by overhead cables. When power needs to be tapped into and used at home, a step-down transformer is used. The principle is the same, except that the second coil in the transformer now has far fewer turns than the first, lowering the voltage to a standard level of 220 to 240 volts. This is a mechanical analogy to the transformer. If vertical displacement can be equated to potential difference, then the torque of the gear is equivalent to current. A large displacement by the small gear will result in a large torque at the other side, in the same way that a large voltage in the primary coil induces a large current and hence less voltage in the secondary coil of a step-down transformer. Higher torque can lift a larger weight but through a smaller distance. Both direct and alternating currents can be used to power electronic devices. Their effect is the same, but their properties are quite different. Take a look at this display. If I draw a magnet next to the DC powered filament, nothing happens. But if I bring it next to the AC powered filament, it oscillates.
When you move a magnet over the AC light bulb, the filament vibrates because of the alternating magnetic field around the filament continuously attracts and repels the permanent magnet. When you move the magnet over the DC light bulb, the filament does not vibrate as there is no change in polarity. The filament will either attract or repel, but will not vibrate. We can now take a look at electricity at home. So now, in an ordinary house, how much energy exactly is being used? At this point, we need to make a distinction between energy and power. Power is the rate at which energy is used. 1 watt is the number of joules of energy used per second. So when we see a 100-watt bulb, for example, it means that every second 100 joules of energy is being used. Now that joule is not the most convenient unit to measure energy. Our electricity meters at home measure the amount of energy in terms of the unit called a watt-hour. Notice the unit is watt-hour, not watt per hour. This is the amount of energy used by a device that runs on 1 watt for 1 hour. From this we can see that 1 joule is the same as 1 watt-second, so a watt-hour is 3600 joules. This display at the museum demonstrates how much energy different appliances around the house use in 1 minute. A microwave oven runs at 120 watts. This means that running it for 1 hour will use 120 watt-hours of energy. Our meter at the display runs for a minute, during which time the microwave oven uses 2 watt-hours of energy. You might be surprised to discover which is the most energy-hungry appliance at home. The rice cooker uses 10 watt-hours of energy in just 1 minute. The LCD TV, on the other hand, uses only 2 watt-hours in 1 minute. It takes 5 times as much energy to cook rice as it does to watch television. An ordinary fan barely uses 1 watt-hour of energy per minute, while our power-hungry hair dryer uses as much as 5 watt-hours of energy per minute.
There are many displays here at the museum dedicated to demonstrating the use of power at home, but perhaps the most exciting is the smart room. The smart room gives us a quick and interesting glimpse into homes of the future, where advanced technology takes us to a new level of comfort and safety. The room is programmed to be unlocked by an authorized fingerprint, which eliminates the need for a key. The act of opening the door sets off an automated switch which controls the lights in the ceiling. Are you tired of turning a room upside down looking for a remote control? The smart room takes care of that too. The television here is activated by sensors in the sofa. This means that it comes on as soon as you sit down. The same goes for the music player, which is similarly activated by the adjacent sofa. As if that isn't enough, the mirror also doubles as a television when someone sits in front of it, so you don't have to miss even a second of your favorite television show. The child's room at the back is kept under constant surveillance with the help of a baby monitor, which beams the signal to a screen. Take a look around. There are many more clever innovations at work in the smart room. We use electricity every day in almost all of our mechanical devices. But we must remember that despite being very convenient and largely safe, electricity does present plenty of hazards if we are not careful. The current passing through here is to the order of picoamperes, which is very, very, very small. But even a mild shock can be very disconcerting.
It is crucial to have a look at the display on electrical safety here at the museum to see how to avoid injuries. When handled with proper care, though, electricity is the safest form of transportable energy available. If a human being comes in contact with electricity from a plug point, the body becomes like a conducting wire to the ground. This is where electricity becomes extremely dangerous. Many electrical devices are earthed, which means that one way or another there is a path of low resistance provided between the circuit and the earth. This ensures that even if someone accidentally touches an exposed part of the circuit, their body does not act as a conductor to the earth, thus minimizing the effect of an electric shock. With so many electronic devices around us, we often encounter the problem of a shortage of power outlets. There is a temptation to connect many appliances to a single power outlet, but this is very dangerous. As we plug in more and more things onto the same outlet, we are increasing the amount of current and therefore the amount of energy coming out. This tends to heat up the wires, and if they get to the point where the insulation is no longer sufficient, they could come in contact with each other. This forms a short circuit which could cause sparks and even a fire. Miniature circuit breakers or MCBs are thus installed to stop current flow if it gets above a certain standard safety level. Mankind has come a long way since the days of candles and firewood. The revolution began with Maxwell's unification, without which no electrical device would exist. Another hugely important consequence of Maxwell's unification is the development of telecommunication. But that is a subject for another time.